if d was 2 here, you know, I would just, my characteristic function would just be such that, you know, if the probability of the outcome of the two outcomes were 1/3 and 2/3, then if x is greater than 1/3, I just give the second outcome. This is essentially all Bell's model amounts to. But you can just sort of formalize it by saying, well, I have some characteristic functions over the space. So diagrammatically, the hidden variable space is, here's the sort of the standard kind of quantum space, the d-dimensional Hilbert space. Here's this distribution x. The probability distribution is a delta function at psi, but uniform over x. And then the characteristic function that corresponds to, let's say, outcome 0 is just sort of a slicing up of the x interval, depending on what the other outcomes are. So you're just sort of slicing up the probabilities. It's exactly what you would do if you're programming MATLAB or something to give you statistical simulation of a quantum system. You would use the RAND generator to produce x. Anyway, so the point is that this model is deterministic. You give me the value of the hidden variable, I can tell you which outcome you're going to get for your measurement. It's highly contextual, that's something I'll get to. And it's psi-ontic. So what do I mean by psi-ontic? Remember, if you tell me that the hidden variable, the value of the hidden variable, in this case, my lambda, remember, is a vector and this real number. If you tell me the hidden variable, then I can tell you what the quantum state was. So these distributions, the p psi and lambdas don't overlap with each other, which is kind of obvious. Each distribution would just be a different slice like this.
I mean, presumably it's not deterministic in its sort of second and third measurements, because you have to presumably choose a new x or something like that.
Yeah, you would have to disturb x. When you do the collapse, you would also disturb x. Okay, so all of the models I've talked about are psi-ontic. Okay. So if I tell you the lambda, then you can determine the quantum state. In fact, if you go through the literature on hidden variable models, and there's a lot, some crazier than others, obviously, so I haven't been through it all. But I think, of course, students have, particularly Nick has. You find that there's only one model which only works in 2 dimensions, which is psi-epistemic. Okay? This is the qubit model that's used by Kochen and Specker in their famous paper proving the Kochen-Specker theorem, that they use to show that the Kochen-Specker theorem doesn't apply to 2-dimensional systems. It only applies in 3 and higher dimensions. So, what is this model? Well, the model's basically like this. Again, the spaces are the same. So the hidden variable space is C2, or let's say the surface of a ball. Okay, the Bloch sphere, if you like to think like a physicist. But what happens is that the probability distributions, so the hidden variables are also vectors in C2. So I'm kind of plotting the 2 spaces on top of each other here. The quantum state in this would be psi, would be some sort of point on the surface of the ball, let's say. The probability distribution in Kochen and Specker's model, in their qubit ontological model, is something which is centered at psi and just kind of falls off like a cosine distribution. I have this normalization on that. But basically you see that it's sort of a cos squared theta. It falls off, it's sort of like this. It falls off and goes down, and it sort of has support only over the hemisphere that's defined by the particular quantum state. Okay? So it's a well-defined normalized probability distribution over the hemisphere that's sort of centered on the quantum state psi. And in this model, a measurement looks a bit like this. So I've drawn the sphere again here. Essentially, the way to think of it is that there's, here you've got this ball, and now the quantum state is, let's say, at the northern hemisphere, but really in the hidden variable model, the system can be anywhere in the northern hemisphere. Let's say the quantum state is at the North Pole. The system in the ontological model could be anywhere in the northern hemisphere with a probability distribution that falls off like a cosine. And then measurements in this model correspond to a bit like you turn a light on and you illuminate one hemisphere. And depending on where you turn that light on, you either see the hidden variable little balls on the sphere or you don't. Okay? So it's like the characteristic functions are sort of all one over a hemisphere. Okay? And as you move this hemisphere around, you sort of can compute what's the probability of of that hemisphere sort of finding the ball that is our value of the hidden variable theory. It's a very simple model. But the way I'd like to phrase it here, I wrote it in terms of step functions because this is how I'm going to generalize it. It sort of makes it sound a bit more complicated than what it is. But basically, if the value of the hidden variable is some point on the sphere, the two projectors that correspond to the measurement are antipodal points on the sphere, right? They're just two orthogonal states. And so, essentially, the hidden variable gives whichever of the two outcomes it's closest to. Okay, so whichever of the two characteristic functions they're defined, it just gives whichever outcome it's closest to. I'm not sure I've explained this model very well. I hope it's semi-clear. But now the interesting thing about this model, of course, is that it's psi epistemic, that if I have this kind of cosine distribution at some point, and then I have another cosine distribution corresponding to a different state, the two non-orthogonal states, the cosine distributions overlap with each other. So it's a model where those distributions overlap. So if I tell you the value of the hidden variable is somewhere in that overlap region, well, you can't tell which quantum state it necessarily corresponds to. So this is the only known psi epistemic model today. Well, this one with this. I have a very stupid model that's sort of psi epistemic. But anyway, this one is nice because it preserves the symmetries of the quantum system and so on.
Sorry,
Yeah.
isn't that the case also for X model?
Sorry?
If you know lambda there, you know nothing about the state. Totally independent.
No, we went through it to try and see. It's not true. So Paul had to go through those things. Ellipsis models are more complicated because they also include the invariables in the apparatus as well as the system. But if you know the real state of affairs of the systems, then you know the quantum state. So, yeah. It's crazy hard. Okay, so what I was messing around with, and this is my failed research program. It's always best to talk about things that you failed at, I guess, in the hopes that someone can help you, is to just try and do a natural generalization for a Q trip. Okay? So I want to take the same kind of thing that Kochen and Specker did, and I say, well, let me try and do a three-dimensional system. But now, my space, I'm going to keep it as three-dimensional vector space. That's fine. So really, there's no hidden variables. The spaces are kind of the same size. I'm going to do like in the Q-bit model. The probability density will be something which falls off. It's sort of centered around the quantum state sign, but it just falls off over some region with some size of support that I've called delta here. And I want to try and reproduce the Born rule with this kind of model. But to do that, I know because of the Kochen and Specker theorem, the same paper that they had the qubit model in, I know that I'm going to have a problem with what's called contextuality. So some people in this audience are experts on contextuality, some might not have even heard of it. So I'm just going to give you a rough flavor of contextuality. So essentially, what contextuality tells us is this. If on my three-dimensional system, I've sort of drawn in real space here, the three orthogonal vectors which correspond to the projectors the three orthogonal projectors of my measurement. It says that any hidden variable model, in order to determine, let's say, whether it's going to give this outcome, which I've labeled 0, it has to know what are the other two projectors which are being measured simultaneously. So if I have, this one orthogonal triad I've drawn here, it doesn't look very orthogonal, and then the one that's rotated, where I keep the state 0 the same here, in the hidden variable model, I need to know that the things being co-measured with 0 are 1 and 2, or 1 prime and 2 prime. Whereas in quantum mechanics, you don't really need to know that. If I tell you the state sign, I say, what's the probability of getting the outcome 0? You don't have to be told, oh, the other 2 projectors are 1 and 2, or 1 prime and 2 prime. So that's my sort of glib summary of what the Kochen and Specker theorem proves, that any hidden variable theory must have this feature, that lambda, you know, if I give you lambda, you better know what the other co-measured projectors are. So now I'm going to give something which Carl Schwartzel to yell at me once in a conference, which is my classical example of contextuality. Okay, so some people believe contextuality is the thing that departs us from anything classical in quantum mechanics. And so saying that you have a classical example of contextuality is it's like red rag to a bull, but this is my kind of classical example. And I'm giving it because I'm going to use a very similar construction in my failed attempt at a Q-trip model. So in this classical model, imagine that I have 3 insulating rods and I stick a positive charge, the same positive charge, on the end of each of them. And this is going to be my measurement device. So, you know, I'm going to send in a charged particle, and depending on which charge it's attracted to. So I'm going to send in some electron, it's going to come along, and depending on which of these guys it's attracted to, then I'm going to say, oh, it gave that outcome. So if it gets attracted to the top one, I say, oh, you know, I measured it as outcome 0. Okay. So it's sort of clear that, well, my electron comes in, as it comes into this arrangement, depending on which guy it's closest to, which of the 3 charges it's closest to, it's going to give that particular outcome. So, yeah, I can sort of divide this region up into, okay, if the electron comes in here, then it'll definitely give this outcome. It's all just kind of deterministic firing electrons into this thing. And you see that if I rotate the charges, okay, so I keep this charge the same, the top one, but I rotate my apparatus, there are some electron trajectories that now would have gone to this charge over here, but instead might go to the upper charge. Okay. So which outcome you get, given a particular electron coming in, which outcome you get depends on the full configuration of the apparatus. It doesn't just depend on knowing that, you know, this charge is there. So there's sort of a region in this space where if the electron comes in sort of, you see this green curve here, if the electron comes in over there, it will essentially always give the upper outcome, the top outcome. But if it comes in somewhere kind of down towards, say, this region that I've colored here, it'll really only give the upper outcome. Sometimes it'll give one of these other outcomes. So it can only know which outcome it's giving if it knows where the other charges are in the space. So I call these sort of regions, okay, faithful regions, the regions that sort of always give that outcome. But then in this kind of space of problems or whatever, there's a bunch of electron trajectories that are unfaithful, that might sometimes go up, but might sometimes go to somewhere else. Okay, so this is my classical example of contextuality. But it's essentially exactly what I'm going to use on my Q trits. Okay? So on my Q trits, I'm going to say, okay, I've got my orthogonal triad that corresponds to the measurement I'm going to do. And I'm going to use a rule which says, okay, you know, given the value of the hidden variable, and remember the value of the hidden variable is also a 3-dimensional complex vector, okay? So I can ask what is its distance to the 3 different projectors. And I'm just going to say, given the value of the hidden variable, it just gives whichever outcome it's closest to. Okay? It's essentially what happened in the Kochen and Specker model. So it's going to have contextuality, because there are going to be some times, so this now is sort of a picture of the Hilbert space instead of 3 classical charges. There's going to be some values of the hidden variable which, you know, are unfaithful. They sometimes give the one projector, sometimes give the other. So it's a contextual model, And so it has some chance of reproducing quantum statistics. Okay. So I can formally write this down as, well, if the quantum projector is onto some state 0, then in my hidden variable model, the characteristic function is only 1 if the value of lambda is closest to the particular state, in this case 0, than it is to the other two. So it's a deterministic contextual hidden variable model. Okay, so let's say you have a model like that. What you want to do is you want to test whether it reproduces the Born rule. So remember, testing whether it reproduces the Born rule is like, well, take the probability distribution, multiply it by the characteristic function, and do the integral. And, you know, it's a very simple space. It's a three-dimensional Hilbert space, so you stick it in Maple when you have no faith in your own abilities to do such integrals. You stick it in Maple. You try and get Maple to do it. You find that Maple can't do it because these kind of step functions are a bit of a mess, and it's hard to break the space up. So you get a bit frustrated with Maple, and so you think, oh, bugger it, I'll stick it in MATLAB, which is really the monkey way of doing it. You know, just randomly sample with some kind of Markov algorithm and see whether I'm reproducing the Born rule, some sort of Monte Carlo algorithm. And that's what I did, and this was the result. So I just randomly chose some different states. You see there psi 1 through psi 5, and some projector. So the left-hand side is kind of a data table for like the quantum predictions, and then on the right is the data table for what this ontological model reproduces if you follow it through like I just did there. And you see that, well, when you first see something like that, your first thought is, I screwed up the programming, or I didn't sample the space enough times, and so on, right? Because it sort of looks like, maybe this ontological model is converging to the quantum predictions. But then you keep running it, and then you realize, no, it's really not. It's getting close, but it's not actually reproducing the Born rule. It's just getting close to the Born rule. So, after more numerical messing around, I sort of found that the largest deviations from the Born rule were if I just took the quantum state to lie in a two-dimensional subspace of the three-dimensional space, and I took the projectors onto 0, 1, and 2. So if I take this to be the quantum state psi, if I vary this state theta, I can ask, what is the ontological model's predictions, this Q-trit model's predictions, which in the standard quantum scenario give the Born rule, give you the standard cos squared theta you would expect. Okay? So the solid lines there are the quantum predictions of cos squared theta, and the dots are the numerics from MATLAB. So you see that this model gets close, but doesn't reproduce the Born rule. Okay? In particular, you see that there's some probability here of getting the outcome pi2, which is always 0 in quantum mechanics, because the quantum state is only in the space in the 0, 1 subspace of the three-dimensional space, whereas in this model you have a non-zero probability just here of sort of a percent or two of getting the outcome 2. Okay, so about 2% is the maximum discrepancy. So if you're like me and you work a lot with experimental physicists, you start thinking to yourself, well, maybe the experimental physicists aren't as good as what people think they are. Maybe there really is a discrepancy. Maybe the Born rule's wrong. Or at least you go to bed thinking that one night. You think, I see all that data they put up at conferences, and they kind of look like cosine curves, but maybe it's this curve instead. So then you really get up the nose of some of your friends by calling them and saying, send me some data that's like the best data you've got, and then they send it to you, and you're like, nah, it's not good enough to do this. And then, fortunately I have quite a few friends who are experimentalists, so they sort of put up with this for a few weeks, and then eventually they managed to convince me that at least this particular model is ruled out by their data. So the biggest problem actually is that there's not a lot of sort of Q-trit systems that people have made measurements of. So no Nobel Prize. Born rule, I think, is still true. Okay, but it sort of bothers me that I can't find a model which does this. It wouldn't have a lot of physics, but just mathematically, it's either possible or it isn't. So the next thing I tried was, I thought, well, this model is particularly ugly because you kind of cook, in the Kochen and Specker model, you cook this cosine distribution over the top of the sphere. Okay? And here I was doing kind of the same thing. I cooked the shape of the probability distribution to try and make it, close to the quantum predictions. And yet, if you really believe in this whole program of quantum states as states of knowledge, you probably should be using some kind of rule, like a maximum entropy rule, to say if I don't know anything about these hidden variables per se, then I probably should be assigning maximum entropy distributions over there. So I messed around with a different model. And in this model, it was the first time that I took the space in the ontological model to be, in this case, one dimension higher than the space in the quantum model. So in this model, the states in the hidden variable theory are kind of vectors in C4. And I take my probability distribution to be uniform in C4 around the point which is sort of remember the quantum state is in 3 dimensions, so it's sort of uniform, centered around the quantum state that's sitting in its 3-dimensional subspace. So uniform with respect to the Hermitian. So again, go through, stick it on MATLAB, and now you find something like this. Okay. So this is kind of a hidden dimension Q-trip model. And again, you see, you get perilously close to the Born rule. But the thing I find interesting about this is now I haven't put in any kind of cosine-shaped distribution. What's happening here is some kind of, I don't know, maybe concentration of measure type effect or something. That it's really the geometry of the 4-dimensional space being projected into 3 dimensions and so on as part of this model gives you something which is, damn close to the Born rule, but still unfortunately not close enough to stimulate people having to do a new experiment. So, you can even do with this hidden dimension, you can do a Q-bit models, because I didn't like the Kochen and Specker model, the fact that they put in this distribution by hand. I thought, well, let me take a 3-dimensional hidden variable space for the 2-dimensional Q-bit and see what happens. And you see again, you get distributions now which are just very close to the quantum predictions, but unfortunately not exactly the same. And all of this is numerics, by the way. I haven't done any of this analytically. But I trust the numerics more than what I would trust my analytic calculations anyway. So that's basically where I'm at with this program. I don't know that it's not possible. Whatever proof that it's not possible there is should try and convince me that you can also bound why I can get so close with these models, which are essentially classical probability theory models, and yet not quite get there. So I think, it's maybe non-trivial to really prove that such a model can't exist. You can certainly put contextuality into these models in a reasonably natural way, and I don't know of any proof that this whole view is untenable. It's still a long way from actual physics, of course. This is really still the mathematical games of what can I mimic in terms of field of space structures. The other thing I'd like to say is that this is at least a quantitative question. There's a lot of, if you go to foundations conferences, as I do occasionally, you find that there's a lot of qualitative arguments. But I think that, at least from the perspective of quantum information theory, what we really want is more quantitative questions. And the last thing we can conclude for sure, because I spent ages on this problem, that answering these questions will require someone who's smarter than me. Thanks.
Are there any questions, comments, views?
Going back to that classical, I'm not sure I understood it right. You were saying that there was this region where there was a bunch of states that would give the same measurement?
Well, it's sort of like this. You've got these 3 things. Let's say an electron's coming in. It's sort of imagine electrons coming in, and then we'll go towards whichever charge is closest to as it comes in. So just imagine it's coming in radially, for example. Now, which charge is close is sort of just a geometrical feature of this arrangement, that which charge is closest to can depend on the actual orientation of these charges. So there's a region here where or let's say region, I'm not drawing particularly well, but there's a region where it's closest to this guy if these are the other two projectors, or where the other two charges are located. But if I rotate it like this charge becomes closer, and so now it goes down like this. So that's a type of it sort of depends on the relative configuration of the apparatus to the particular state of the electron. They said this is a classical electron, no quantum mechanics here. I'm just talking about a charge coming in. Right? So it's a type of, and it's clear that sort of gives you. So now I translate that to the three-dimensional Hilbert space. It gives you a type of contextuality that at least conforms with the geometrical structure of the space to some extent. Like it has sort of easily defined properties in terms of the geometry of the space. So it just seemed like a good place to start, because actually finding contextual things, I mean, Bell's model is contextual, but it's not a psi-epistemic model. These models that I've talked about, or the ones I'm interested in, are psi-epistemic. They're really proper probability distributions that overlap with each other. But yeah, sort of, finding ways of implementing contextuality in a sort of semi-natural way.
No, I mean, what was the quantum mechanics? Then I remember you labeled each of them as a state in the next slide.
Yeah, so now what I do is I say, okay, it's basically an analogy. So now I have the three orthogonal states that correspond to the projectors of the measurement. I still have a notion of distance because I'm in this Hilbert space. It's sort of essentially one, the Hilbert-Schmidt distance or something. So I can just say, given the value of the hidden variable, which of these three projectors is it closest to? The same as the classical charge would go to whichever charge it was closest to. Now my hidden variable is a vector in the space. These are vectors in space. I can say, okay, it gives whichever outcome it's closest to. And that's a contextual assignment of it depends on what the other two projectors are, which guy is closest to in the Hilbert space.
So this is kind of a hidden variable model.
Yeah, except that the spaces are the same, so nothing's really hidden.
Thanks.
Yeah. I've got a comment that is also an offer actually because we have a bit of free time. In the Topos approach, we can show that we can actually write quantum states as, well, what you would call probability distributions. Actually, it's proper measures. They do not live on a set, they live on some other structure. And if you do this, if you allow for something more general than a set as the carrier of your probability distribution, you can actually get a one-to-one correspondence between probability measures and quantum states, and the Born rule holds and all this stuff holds. The offer would be to the audience, if you like, I mean, we have a lot of time, I could talk about this.
Yeah.
I think it ties in quite neatly with what you said, that if someone's not interested, I don't mind if you're leaving and have a long break. But I think I could easily do this in 30 or 40 minutes.
13?
30 or 40.
13,
Yeah.
Like talk and like after Leo's then.
Oh, now.
No,
no.
right now. Ego is not coming, so this would be the free slot now. You can either have a very long break now, which doesn't seem really necessary, but I don't know. It's an offer. It's not.
Has an overlap. Whereas I think when you do these epsilon things, it might not work like that. It might be that only the ones that are close have an overlap or something like that.
Even if you do have an overlap, might you not get some sort of information leakage by just applying Bayesian stuff to what you get?
Yeah, but I think if you
there must be constraints on that sort of leakage as well, rather than just overlap or non-overlap.
So I think the sort of I don't mind that too much. What I suspect, though, is that if you're reproducing the Born rule, that the information you gain will be the same as if you did the optimal quantum measurement for distinguishing the two states. You know? So that really, somehow, the fidelity of the overlap in these distributions will match what you know, when you're doing the optimal measurement for distinguishing two classical distributions, you should, when you Bayesian invert it, get the same kind of a posteriori distribution as you would quantum on the two states. That's just a hopeful case.
I'm guessing from the way you laid out the mathematical formalism that you're deliberately not concerned with the geographical layout in space of the different degrees of freedom. Like, you know, if it's an 8-dimensional thing, it may be laid out as 3 qubits in wildly separated locations, or it may just be laid out as 1 qubit octet in one location. You're deliberately not caring about that.
Because at the moment I'm only working on 3-dimensional things, and you know, space is just a basis.
Okay.
It'll be a different basis.
Is that the beginnings of the answer to your earlier puzzle? If you exempt yourself from locality worries by trying to get to something, then...
Yeah, I mean, so I think... So once you convince yourself that this is possible with this puzzle, as it were, you realize that, okay, so the reason that we believe quantum mechanics, well, you know, if you want to be a pure mathematician, you say, but what you haven't done is taken into account the tensor product structure of like separated systems should be described by measurements that commute, for example. When you add that, you suddenly can't reproduce every data table by overlaps. So then you say to yourself as a physicist, is that really why I believe quantum mechanics? Because if I add this assumption that these particular mathematical objects commute when I do these spatially separated measurements, and I think as you ponder more and more on this, you know, you realize that the reason, at least that I believe quantum mechanics, is actually to do with canonical quantization. The reason I believe quantum mechanics is I can take a Hamiltonian from classical physics that I know describes particular situations, I follow a quantization procedure, and I see the spectral lines that come out of a sodium lamp or come from the stars. That's really what convinces me that quantum mechanics is true. And that's because I'm not going to the complete mathematical abstraction of allowing arbitrary unitary transformations and arbitrary Hamiltonians, but I'm looking at the things that I know kind of describe aspects of the world around me, and I have a consistent procedure for sort of going into the subset of Hilbert space of Hilbert spaces that describe that. And so I don't believe quantum mechanics because of sort of empirical data tables and probabilistic things like the Born rule being reproduced per se.
Okay, that doesn't mean you have to play with temporary A, but pretending to be a classical physicist, writing down a Hamiltonian that would be plausible in a classical world.
And we've been doing this for, 80-odd years, and
no, I know.
we don't have anything better to say about that. But hopefully, if we one day have a deeper understanding of quantum mechanics, we will understand why that procedure works better.
Yeah, I
So-
got one.
Sorry.
So why the insistence on these overlaps?
Just because of this issue of, if you don't have the overlaps, then I can say, well, why not just treat the quantum state as a real thing? Okay? Because I might as well just say this region of hidden variables, replace it by this vector in this Hilbert space. And so then you come to this, you need to read, I don't know, say Rob Specker's papers on, like, what are the arguments for the quantum state being a state of knowledge or a state of information? And things like, you end up with a drastic non-locality. You have this quantum state in this 4-dimensional space, you make a measurement and you immediately change the state over there, and so you lose this analogy with kind of measurements on classically correlated distributions and so on. So, yeah, it's a philosophical position that we're trying to underpin with some